Good evening and welcome again. My name is Liam Kennedy and I warmly welcome you to another episode of Look Up Tonight. Yes, this is the cable show of the Orange County Astronomers, and we are the largest astronomy club in the country, and we invite you one and all to watch our show and learn what our club is all about. Our monthly meetings are open to the general public, so feel free to come down and join us at our next meeting in March. It'll be great to see you there. The following presentation is by Dr. Gary Peterson, Professor of Geology for the past 30 years at San Diego State University. Dr. Peterson discusses what we know about the development of the oceans and atmospheres of Venus and Mars, and how that information allows us to predict the future of Earth's own ocean and atmosphere. Here is Dr. Peterson.
What I tried to do was to use my knowledge and understanding of the Earth in order to interpret what I would see. And this is a very interesting thing to do, and I've presented a lot of things to you here along that line. I think I really had a kind of a big breakthrough in understanding when I began to ask the question, well, if all these things are formed in the same way, and if they're all formed at the same time, and if they're all formed out of the same thing, the planets, then why are they so different? And, you come to gradually realize that, well, the reason for the difference is that what you're looking at is how they have evolved over the last 4.5 billion years. Each in its own way, depending on the size or the mass of the planet, and then also depending on the distance from the sun. And once you understand this, understanding the planets just becomes absolutely amazing, and just wonderful. Then there's another thing that set in, and that is, although I started out using my understanding of the Earth, what has happened is gaining an understanding of the solar system has told me things about the Earth that I would never even have dreamt. And that's what I'd like to tell you about tonight. So what I'm going to do, and this may be a little bit duplicating for some of you that have heard some of my other talks, but I think you can, just be patient. What I would like to do is to explain to you my understanding of how the planets are put together, and then go to how it is that they change into their present form. And my goal is to tell you something about the Earth that I'll bet you've never heard before, or I'll bet you've never guessed. Okay, I thought I'd start out with a couple of the basic building blocks of the solar system, and one of them, of course, is asteroids. So I would use this as an example of an asteroid. I don't know, it's about 15 kilometers along. It's a big chunk of rock. They describe them as being potato-shaped, and then it has all sorts of nicks and dents in it. This is the asteroid Gaspra. And then these asteroids are collected into larger and larger clumps, and when the clumps get large enough, we refer to them as a planet. And then I'll use the planet Mercury as an example of this. And then when you look at Mercury, or some of the relatively primitive planets, the moon is another good example. While you see this pockmarked surface all over it, these are explosion basins signifying the arrival of an asteroid. And then when you look at this, please realize that you're out at great distance. So these basins may be 100, 150 kilometers in diameter, so they're really quite large. And as you get closer, you would see smaller and smaller and smaller and smaller ones. Now, when you look at that, then what you're looking at is whenever an asteroid arrives and impacts onto the surface, then the planet is one asteroid larger. You see, and you just look at all of that. It doesn't have to be an asteroid. Anything. An asteroid, a grain of sand, a speck of dust, a meteorite, whatever it is, then the planet is larger. So when we look at this, what we're looking at is the last arrivals. Let me indicate also that another way that you really should be looking at this is that when an asteroid arrives, not only does Mercury become one asteroid larger, but then equally important, the solar system then has one less asteroid. See, so the planets are the solar system's way of cleaning up the environment. You know, the environment that is left over after the formation of the sun. You get all the debris centered around in these large clumps. Now, another thing that happens is that when I talk about asteroids colliding with planets, there's basically only about 9 objects that they can collide with, you know, so they also collide with one another, but we don't have any images of that happening. So I'll have to go to one of these astronomical art types of things. Very dramatic appearing thing where an asteroid runs into another asteroid. And I imagine that's fairly frequent simply because there's so many asteroids. There are tens and tens of thousands and so on. So when asteroids run into one another like this, they can totally obliterate or shatter the asteroids. And then this gives rise to all kinds of debris, ranging anywhere from fairly large chunks to small pieces to dust particles, you know, the entire range of things. And then all of this kind of grit that is out there in the solar system, this grit comes in and impacts on our planet too. And people who think about this have estimated, for example, that every day approximately 1 million kilograms of this finer grit arrives at the Earth in the form of dust and meteorites and stuff like that. 1 million kilograms per day. You know, and that's such it's spread over the entire Earth, of course, that's very small, but taking it in a longer context, there's probably more of this fine material arriving at the surface of the Earth than there are asteroids. And that adds to the size of the total Earth. When you think about this, then asteroids are being destroyed in 2 different ways. One of which is they're running into the planets and forming ever larger planets, and then the other of which is they're running into one another and creating all this fine grit, which ultimately probably most of it ends up on the planets. So if we're right here at 0, and then we count backwards into the history of the solar system over 4.5 billion years, if we know the rate at which this is happening, and we really don't, but I mean, that's easy to imagine that an asteroid impact might be once every 1,000 years or something like that for the entire solar system. Then if you count backwards in the history of the solar system, you have ever more asteroids, and more and more and more and more and more, until finally when you get back to the time when the solar system first began, then you have all the asteroids in the solar system that were left over after the formation of the sun. And when you have that many asteroids, then the collision rate is many, many times higher. That is, you might have 10 times the asteroids of the present. You might have 100 times the asteroids of the present. It's kind of hard to tell. But when you have that many asteroids, then your impact rate is very, very high. And that's where the planets come together, is in the initial collection of the asteroids very early in the history of the solar system. And as all these things collide and come together, then you decrease the number of asteroids. So as the asteroids are used up, then you go down this curve down here, and the impact rate becomes less and less and less and less, until finally, when you get down to the present time here, maybe our impact rate is once every 1,000 years or something like that for all of the planets. Now let's add to this a bit, because the other basic building block of the solar system are the comets. And very early in the history of the sun went through a real high energy phase, resulting in the formation of the asteroids. And at this time, it drove the volatile constituents, that is, the things which would be liquids or gases and so on, it drove them out and away from the sun. And those that didn't collect as a part of the gaseous giants, but rather expanded out into the colder and colder part of the solar system, then condensed like hailstones. And these hailstones are known as comets. I got this illustration from a Scientific American, and it has a lot of flaws in it, and yet I'd like to use it as a classroom teaching type of thing. So all of the planets now are within this little part in here. All of the planets, and then you get out of there, there's a sort of a concentration of comets out and beyond Pluto, the Kuiper belt, and then the comets range all the way out, I guess out about as far as Pluto is from the sun, and this is known as the Oort cloud. Now there's a lot of flaws in this diagram. Of course, we don't really know how many comets are in the Oort cloud, but I guess Oort had estimated about 200 million or something like that, and I've seen higher estimates and I've seen lower estimates, and I don't know which one to believe in. But the comets certainly wouldn't be large enough to see, and then they wouldn't glow. So it's kind of very misleading, but I still like the diagram, you know, and I get a lot of use out of it. Then in addition to this, all of this stuff is in orbit about the sun, except the orbit is so large that it might take 4,000 years, 4,000 years for a trip around the sun or so on. And in here there's some larger objects. I guess the trans-Neptunian objects, they're referred to nowadays, or minor planets if you prefer. And I guess a couple hundred of these larger objects have been detected, and some of them get up to, the latest figure I saw was about 600 miles in diameter. And when these smaller objects come close to a larger object, why, they can get their orbit bent, and then in bending the orbit, they come into a real nice elliptical orbit and go down into the interior of the solar system. And next slide here. And then coming down into the interior of the solar system, they get heated up, and these are basically just pieces of ice with a lot of exterior coating, 4.5 billion years of exterior coating on them. And when they come into the inner solar system, they get heated up by the sun, which then tends to drive off the volatile constituents and form a little bit of an atmosphere around the nucleus of this particle of ice. And then the outflow of the sun's energy strips off this little atmosphere to give you your nice tail on out in that direction. Now that particular one you'll recognize as Halley's Comet. And the reason I used Halley's Comet is that it's what is referred to as a short period comet, comes back about every 76 years. And then when you know that it comes back, and it's readily predictable that it comes back, then you can get your grant proposals together, and you can, write what you're going to do, and you can get your spacecraft ready to go, and all of these things which take an immense amount of time and effort, and then you can go up and have a look at it. And the last time that Halley's Comet was here, there was a regular armada of spacecraft which went up and took a look at it, and flew right up into its little atmosphere and analyzed what the atmosphere was. Next slide. See, and here's a list of things that were found in the atmosphere. Let's see, there we are. Okay, there's some metals and stuff like this, and this is probably coming out of accumulated dust that is along with the ice. And then there's a whole host of these volatile constituents here. And basically, these are just molecules and ions of the common things that make gases. Carbon, oxygen, hydrogen, nitrogen, sulfur, all sorts of things like this. And anyway, when you look at this, there's just about every constituent in there that you would want to make up an atmosphere of a planet. And then this is just a list of things that have been identified. People who work with this say that about 80% of the stuff is water ice, and then there's also ammonia ice and methane ice and a whole host of other more minor constituents in there. Now, one thing is that when you get a comet like this, it is always giving off these constituents, and then the constituents are always being stripped away, then the comet has a finite lifespan. Like Halley's, it's not going to last forever. They estimate that comets might have a lifespan of about 500 trips through the inner part of the solar system, and that would mean that Halley's Comet would last for about 15,000 years, somewhere like that, until it ceases to exist as a comet. And then when it ceases to exist as a comet, it might continue its journey as a bunch of debris. And next slide. And then the debris can come into the atmosphere of the Earth, you see, and look like one of these meteor showers or something like that. Somehow they never look quite that good when I look at them. As a matter of fact, I'm lucky to see 3 or 4, but I understand that some of these storms are really spectacular, and this is a woodcut that goes back to great antiquity. Anyway, that's also adding to the Earth, you see, and what that's adding is the constituents of the Oort cloud are being added to the total storehouse of stuff that we have on the Earth. Okay, next slide. Now let's go to our recent visitor here of Hale-Bopp, which is just a wonderful, wonderful event. I feel so privileged to have seen that. Anyway, it's a fairly good-sized one, and it was fairly close, and it received a lot of study. And I should mention that this is a long-period comet, that originally had an orbit of about once every 3,000 years. And when you take one of these long-period comets, if it makes 500 trips, then it would have a lifespan of about 1.5 million years before it finally ceased to be a comet by letting off all of its volatile constituents. This particular one is estimated to have a diameter of about 40 kilometers. And then if it's roughly spherical in shape, why then it would have a volume of something like 40 to 50,000 cubic kilometers, and 80% of that would be water. And that doesn't mean anything to you, but 40 to 50,000 cubic kilometers of water would equal all the water you could fit in all the Great Lake basins combined are tied up in that one comet. Plus, there's all kinds of other gases, and plus there's the rind around the comet, too. In any case, things like that are coming down in through the solar system, and I go to the next map here that I have. And this one came through in here. It came from the southern hemisphere of the solar system, and then passed reasonably closely to Jupiter, where it got its orbit bent a little bit, so it'll be back once every 2,000 years from here on out. And then it came through the northern hemisphere and passed by the Earth and went down into the southern hemisphere and departed in this way. And I guess from the southern hemisphere you could see it for some time after we could in the northern hemisphere here. Well, then a diagram like this suggests another possible demise of a comet, and that is that the comet could run into any of these planets. And the diagram here, which is made up like this, is so terribly misleading because it's not drawn to scale. But I don't know what you would do. If you drew the thing to scale, you couldn't see the planets on there. And then if you drew it to scale, the comet itself would be about the size of one electron. So you gotta present it like that. But this greatly overstates the probability of a collision when you look at these diagrams. However, during a typical year, let's say it this way, about once every 3 years, a comet will come around that is large enough and bright enough that you can see with your unaided eye. But those of you that are into watching comets know that during a typical year, maybe 20 or 30 comets would come in and through the solar system like this. So that increases the odds of comet and planet collisions. Now, I don't know exactly what the collision rate is. There's a rate which was stated, and I think it's just an educated guess, that maybe about once every 1,000 years, one of these comets that are coming through the inner solar system might collide with a planet. Now, that would mean, during the millennium, 20 to 30,000 comets would come through here, and then maybe one of them would collide. I suspect the collision rate is a little higher than that. Next slide. I guess the only reason is I heard that estimate, and then about 5 years after I heard it, we in fact had a collision. I guess that doesn't mean anything, does it? Because it's just one collision. But it's just a wonderful event. And Comet Shoemaker-Levy 9 made a very close pass to Jupiter, and Jupiter bent its orbit big time. And I guess as it went around the corner, it broke up into a whole string of things, string of pearls, they like to call it. And it raced out and tried to get away from Jupiter, but just couldn't get away. It went all the way out and then turned around, and then all those things came back in and just drilled Jupiter across the southern hemisphere like that. Just a wonderful event. Well, we see so many collision types of things that are formed by collision, but that's really the only actual collision that has ever been observed, and that's a neat thing. Now, what I would emphasize on that is that whatever Shoemaker-Levy 9 was made out of, that is now a part of Jupiter. Not that it makes much difference, but, see, that's a way that you take the constituents of the Oort cloud and you apply them to a planetary surface, and it becomes a part of the planet. Okay, let's go to the next slide. Now, if we have comets, and comets are destroyed in two different ways, one of which is once they make their appearance within the inner solar system, then they have about a lifespan of about 500 trips through the inner solar system, either 15,000 years or a minute or 500,000 years, something like that. Okay, that's one way that they are destroyed. The other way they're destroyed is if they run into a planet, and that might happen once every 1,000 years, although I suspect it's a little higher. So however many comets we might have at this particular time, and I don't think we really know, but let's just use Oort's guess of about 200 million. Then if you know the rate at which they're being destroyed, as you go backwards into the history of the solar system, you have more and more and more and more and more and more comets. You see, so when you get back to the beginnings of the solar system, when the comets were first formed, while you may have 10 times as many as you have right now. You may have 100 times as many as you have now. And when you have that many more comets, then the rate at which they're colliding is much, much higher than it is right now. So, just like asteroids, the comets would be colliding with the planets at a very high rate. Oh, I don't know what the rate would be. Maybe it might be once every 100 years, maybe it might be once every 10 years, but that would be a very, very high rate in the earliest history of the solar system. And if you're going to use comets as a source for atmospheres and oceans, then the atmospheres and oceans occur very early in the history of the solar system. And all of our knowledge of the Earth and the other planets suggests that that is in fact the case. Next slide. Now, here's one from a basic geology textbook. And I'm almost ashamed to admit this, because I used to teach this stuff for years and years and years, see? And geologists believe, and they still do, 99% of them, they believe that the atmosphere and the ocean is a product of outgassing, of volcanic outgassing. Maybe you've taken a geology course and you've seen this. It's totally logical, because you can go to any volcano that you like, and you can examine the stuff which is coming out of it, and there's all kinds of gases and water and all sorts of things coming out of here and being dumped into the atmosphere, and then these ingredients react with other things, and the ingredients condense to form water and stuff like that. And I have nothing against that. Nothing whatsoever, because it can be observed. Next slide. Outgassing. See? You know, there it is. Voluminous quantities of gases coming out of the interior of the Earth and emptying out into the atmosphere. Okay, next slide. The thing that I would like to point out, however, is that you see here's one of these volcanoes, like St. Helens. Here they are. And these volcanoes are formed by a process that geologists refer to as subduction. And you take the ocean floor, you see like this, the ocean lithosphere, if you like, and you subduct it down into the interior of the Earth. And when it gets down into the interior, then melts arise and come to the surface, and they erupt as volcanoes. Well, you can't get rocks that are any more saturated with volatiles than those. And when you take those down into the interior of the Earth, they just come right back to the surface. See, it's a recycling operation, isn't it? Okay, and then what doesn't come back to the surface like this in the vicinities of these types of volcanoes goes deep down into the mantle, and it gets stirred into the mantle, and it comes up as gases in volcanoes all over the world. See that those gases are coming up. They've been at the surface of the Earth before, most of them. Okay, now while I have this on here, I'd like to also say that this same process of subduction results in the production of these things that don't reach the surface. They're called intrusions, granitic intrusions, and they would come up and they would solidify beneath the surface, but they're also the same thing. This diagram is a little misleading because it shows, all these volcanoes erupting, whereas in reality, about 90% of the melt which comes up here doesn't reach the surface. It cools and crystallizes beneath the surface. Next slide. Okay, and then when we can go to some of these granitic rocks, this is a locality that's way up in what is known as the Slave Province of Canada, and they're granitic rocks, and they're granitic rocks just the same as you find around here in the hills around Orange County and San Diego County and so on. They're exactly the same. The difference is that these are the oldest known rocks in the world, and these are 3.96 billion years old. 3.96 billion. And they're granitic rocks. And what that would be important for is that kind of rocks are formed by subduction. See, so as far back in the Earth history as you can go, you've always had these plates moving in and subducting down into the Earth, and then the volcanoes bring all this stuff back up to the surface, all these gases back up to the surface, and they distribute them. Okay, now I have nothing against outgassing, because it in fact is happening. It's just that I don't think that's the main way that we get our oceans and atmospheres. I think the main way we get them is through the impacts of comets. Next slide. See, like if we go to a graph like this thing is based on radioactivity, radioactive decay, which we can measure the rate of. So that, for example, if we just take one example, like the potassium-argon reaction. And if we say we have a certain amount of potassium here, and we know that it decays with a half-life of 1.3 billion years, then according to that, if we go back 1.3 billion years, then we have twice as much of it. And if we go back 2.6 billion years, then we have 4 times as much of it. And if we go back 3.9 billion years, then we have 8 times as much of it. And if we go back to the beginnings of the Earth, we might have 13 or 14 times as much radiogenic potassium as we have in the present environment. And that's just one radioactive series. Do that with every radioactive series you can think of. And what you find is that very early in the history of the Earth was much, much, much more radioactive than it is at the present time. And the radioactivity is the main source of internal heat for the Earth. So this graph is constructed along that line, and it gives it here in a figure here, but you don't have to know anything about the figure. You can say, well, if the graph is correct, then the present day heat production in the Earth is approximately 1/5 of the heat production in the Earth when the Earth first originated. 1/5. And that is so much heat in the early history of the Earth that some people think in the earliest history of the Earth was essentially molten with only a very thin outer crust on it. Okay, now the reason I would bring this up is that if you want to talk about outgassing, this is the time that outgassing takes place. This is the time when the gases and water and stuff is driven out of the accumulated asteroids. And I have nothing against that, okay? Now, I would estimate you only have two sources of gases and water. One is outgassing, like this, and the other is comets, the impact of comets. And at the present time, I think that perhaps about 3/4 of our atmosphere and ocean type of constituents comes from comets, and about 1/4 comes from outgassing. Next slide. Now, once this happens early in the history, all of these things happen very early in the history of the solar system. Now, the next question would be, well, what happens to those constituents? And I think you can understand this if you look at the mass of the planets. And that is, the mass of the planets here are set, the Earth is set as 1, and then everything else is a percent of that. So if the Earth is set as 1, the Moon consists of 1.2% the mass of the Earth. Why, that's tiny. Or Mercury is only 5.5% the mass of the Earth. See, things that are this small just can't set up a large enough gravitational field that they can hold water and gases. So whether it's formed by outgassing or whether it's formed by comet impacts, these real small objects like this just can't hold it. Whatever gases are released, those gases are stripped off, just like gases are stripped off a comet in exactly the same way. Now you go to the other end of this and you look at something like Venus or the Earth. Now these things have real heft. I mean, they're getting up to the size where they can hold all gases except 2. And the 2 that they can't hold and that will drift off are hydrogen, the lightest gas, and helium, the next lightest gas. Those will drift away and leave the planet. There's a big gap up to the next ones, and all other ones are hefty enough that they will stay with the planet throughout the history of the planet. Okay. Now, then let's go to these two larger ones, the Earth and Venus. Next slide. Well, they're about the same size and have many similar characteristics, but then they're drastically different in some sorts of ways. Venus is sort of like an example of Hades, you know, and then whenever you read about Venus, you know, you hear about these horrendous temperatures, 900 degrees Fahrenheit average temperature on the surface and stuff like that. And then another thing you might read is that Venus has an atmosphere which is 92 times as dense as that of the Earth. Okay, now I want to explore those two things, because a lot of people say that this is due to a runaway greenhouse effect on Venus. But I think the real culprit here is the rotation rate on Venus. If we say that 1 turn of the Earth equals 1 day, okay, then the Venus day is 243 days long. It's rotating that slowly in a slightly retrograde manner. Now what that would do is, well, could you imagine if the Earth was doing that? You know, I have trouble making it through a 12-hour day of sunlight. If you had sunlight on the Earth of 120 days duration, you'd have the water on one side of the Earth boiling and the water on the other side of the Earth frozen solid. You know, and that's exactly what's happening to Venus, except it's happening on a more dramatic scale because it's closer to the sun. I think the main culprit here is the rotation rate. Okay, now, next slide. When you've got a turn toward the sun like that, the sunlight, particularly ultraviolet light, comes in and goes through the water vapor, which it has generated because the water is boiling, and it takes water vapor and it breaks it down into its constituent parts. It breaks it into hydrogen, and of course the hydrogen is so light that it immediately drifts off, and it breaks it into oxygen, and then the oxygen reacts with any other thing that it can, such as methane or nitrogen, and the end product of this reaction is an atmosphere which is made out of carbon dioxide and nitrogen. And that's exactly what the atmosphere of Venus is, carbon dioxide and nitrogen. Next slide. Okay, and then here's a listing of the Venus atmosphere. See, 96% carbon dioxide, 3% nitrogen. Every other ingredient in the Venus atmosphere is just 1% of the total atmosphere. However, I would emphasize that if something has an atmosphere that is 92 times as dense as that of the Earth, then 1% of the Venus atmosphere is just about as dense as the Earth atmosphere. And there's a lot of noxious stuff in there. Okay? Now, when you look at that, I guess if you know anything about the Earth's atmosphere, you might spot this nitrogen and say, oh, well, there's only 3% nitrogen. Why doesn't it have as much nitrogen as we do? It does. 3% of an atmosphere that is 92 times as dense of that of the Earth is approximately the same amount of nitrogen that the Earth has. Just about the same. And nitrogen is an interesting one because it acts as an inert gas. It doesn't combine with anything to any degree. So the Earth and Venus have just about the same amount of nitrogen, even though as a percent it looks vastly different. The real question is, why doesn't the Earth have so much carbon dioxide? And there's a real simple answer to it. Next slide. The Earth has a way of storing things. Like look at the way the Earth stores oxygen and carbon dioxide. That is, all the iron ore in the world is stored oxygen. Anything that you see that is red is stored oxygen. Carbonate rocks are stored carbon dioxide and stored oxygen. All fossil fuels are stored ingredients like this. All natural gas, stored ingredients. Look at all the water and ice and everything we've got on the Earth. See, and that's unprocessed oxygen. It still is bound to its hydrogen. All life is made mostly out of gases. I guess we're reminded of that every once in a while when somebody is cremated, you see, and you end up with a small pile of ashes and the rest has been returned to the atmosphere. Or like when we have the wildfires in Southern California and they come sweeping through town, and leave a little pile of ashes where the house once was. Okay, all those organic constituents in the house are now back part of the atmosphere. All kinds of rocks store this stuff. See, you could probably add to this list, but if you take all of these things that are stored, they're all stored atmospheres. Most of them are stored oxygen and stored carbon dioxide. And if you could regasify all of these things, the Earth would have an atmosphere which was denser than Venus by a little bit. So they really aren't that different. It's just that the Earth has a way of storing things. Venus doesn't. Next slide. Okay, then we look at the Earth. Look at the stored water. Just an amazing amount of stored water. See, that's unprocessed. On Venus, it's all been processed. And then if you look at the atmosphere on the Earth, we have a nitrogen atmosphere except for one other main ingredient. And the other main ingredient is oxygen. So next slide. And oxygen is produced by life. See, oxygen, photosynthetic things, real simple kinds of life and on up through plants, take in whatever carbon dioxide they can take, and together with water, they put it through the process of photosynthesis to create their organic compounds and so on, and then they release oxygen as a byproduct like this. And out of our atmospheric constituent of oxygen, All but about 1% is manufactured by photosynthetic life. The other 1% is manufactured by photochemical dissociation. So next slide. Now, when we look at the surface atmosphere on the Earth, I'm sorry about that misspelling there. I got it on the slide and haven't had a chance to take it off. But when we look at the atmosphere of the Earth, you see we have this nitrogen making up 78% because it won't combine with anything in any quantity. So it stays in the atmosphere. And then we have oxygen making up 21%, and 20 of that 21% is made up by life. And then all other constituents, taken together, the water vapor is variable. So all things except water vapor constitute about 1% of the atmosphere. Next slide. Okay, now, once we know that, let's go to Mars. Very interesting place these days, especially these days. And early in its history, Mars had an ocean. And I have no doubt about that. And the ocean was approximately in this configuration. Now, this is just an artistic creation, and the artist here simply colored in the lowlands of Mars. See, with this nice illustration. Colored in the lowlands, put in a few atmospheric effects, etc. For orientation, I guess the Opportunity lander is kind of right over in this area. Okay, now, let's look at it in a little bit different way. Let's go to the next slide. In this way, Mars is rotated so that you're looking at the North Pole. And then in looking at the North Pole and using this topographic map, which is made up here, the ocean was in what is referred to as the northern lowlands, primarily, right in here. Now, if that topography, the dark lines on here are positions where people have estimated that there might be shorelines. Now, if this topography is accurate at all, and I really think that it is, then you look down here on the scale, and what you find is that ocean was about 4 kilometers deep. 4 kilometers. The Earth's ocean is only 5 kilometers deep on the average. That's astonishing. But I'm absolutely convinced of it. And let me show you one of the many ways in which I'm convinced of it. Let's say, because I'm a geologist, let's go to a geological thing. Let's say, what kind of evidence would you look for in this northern lowland? Okay, next slide. I go to something which is common to everyone's experience. And that is when you have a pond of water and the pond of water dries out, it produces these shrinkage cracks like this. And you can refer to these as desiccation polygons. See? And everyone has seen them in one place or another. Okay, now what most people have no idea of is that these occur in all scales. So when you're looking at this, see, you're looking at the big ones. Well, why don't you look at the little ones? See the little ones all over here? Okay, because they occur at all scales. And then if you get into looking at desiccation polygons, instead of being right down here on the ground, why don't you get up in an airplane and look at them, like on this next slide? See, now you're in Rogers Dry Lake here in California. And then from these fractures, between the two arrows, is 80 meters. And if you went down on the ground and you looked, you'd find the ones of smaller scales. Now, I started looking around, and I found that here in California, we have these desiccation polygons that are as much as 2.5 kilometers from the boundary on one side to the boundary on the other side. But I chose to use this slide because this is a particularly good one that's kind of close to the hypothetical shape that they ought to have. Ideally, they would be hexagonal in outline, and that's really nice. Okay, now if you go down to the ground and look at them, next slide. See, here's a geologist examining one of them, and this is in Antelope Dry Lake. You know, they used to think these things were formed by earthquakes. And they aren't. They're formed by the Los Angeles Water Diversion Project. See, you take all the water out of a natural system, and then you lower the water table in all those dry lakes, and the dry lakes dry out, and when they dry out, they give rise to these fractures like this. And then see here, this photo didn't turn out ideal, but see the smaller scale over here? Okay, now next slide. This is Mars. And that's in the northern lowlands, where the ocean basin was thought to exist, where I know it exists, okay? Now, when you look at that, I want you to look at a couple different things on that. First of all, take the desiccation polygons out of your mind, and when you do, you notice that you've got a flat surface there. There are no craters. Your original cratered terrain is not present. You see, well, that's what you would expect to have at the bottom of an ocean, a flat abyssal plain, a flat, featureless abyssal plain, just like we have in the earthly ocean. Okay, then when that flat abyssal plain dries out, then you produce these big polygons, like this. Okay, now if we went down to this, I would expect to find smaller and smaller and smaller polygons. When you look at these photographs of Mars, I want you to look at the Opportunity landing site and see if you don't see finely stratified sedimentary rock, and see if those fractures don't look like desiccation polygons to you. I haven't seen that in the news anywhere. Just check it out, okay? Now, after these desiccation polygons formed, then you get these little craters all over it. Well, these little craters are the last of the debris which is coming in, see, and they're going to pockmark the surface all over here. And then people who study those little craters like that, they say, well, based on the number, based on the size and the distribution, that dried out maybe 1.5 billion or maybe 2 billion years ago. Something like that. Okay, next slide. I just want to drill this in, because I read a lot of funny things in the newspaper. Have you read the ongoing story about how scientists are going to Mars to see if they can prove that Mars once had water and once was much warmer? Everyone knows that, don't they? We've known that for 25 years. All you got to do is look at this. What do you think this is? See, that's what happened when rain falls in faster than it can sink in. It runs off, and it gives you drainage. And that drainage is just like the drainage that you have on the Earth in dry regions. Just exactly. We call it dendritic drainage, But I mean, look at how the streams run down and they all gather into larger and larger streams and so on. See, that's an indication of running water. There's no doubt about it. And the people have tried to explain this away in so many different ways, Like I've actually heard scientists say, well, you can't prove that's water. Maybe it's some other kind of fluid. What other kind of fluid? Water is the only kind of fluid that exists in this part of the solar system. Now, let's say it's water, okay? So let's just say, all right, don't beat it to death. It's water. Okay, if you agree that's water, then you've also agreed that Mars was once much warmer than it is at the present time. Because at the present time, the average surface temperature is minus 50 degrees Celsius, and under those conditions, water doesn't run. Water is frozen solid. Okay, let's say that you've agreed. Okay, it's running water. Okay, then you've agreed with me. Let's say that then you've agreed with me that Mars once had a much denser atmosphere than it has at the present time. because at the present time it has an atmosphere that is 0.07 bars. And under those conditions, water cannot exist as a fluid. Water can only exist as a vapor or as a solid. So if you think those are produced by running water, you have automatically bought that Mars was once much warmer and had a much denser atmosphere. You know, just the thing that they're trying to prove in the newspaper. Okay, next slide. Now let's take a look. Let's go back to this one here. We said we start out with two planets that are so small that they can't hold anything. Everything drifts off. And then we go to two planets that are so large that the only thing that can drift off is hydrogen and helium, but it can retain everything else. And then look where Mars is. It's in the middle. And then it's enhanced by being farther out in the solar system, you know, farther away from a good source of energy. So see, everything is logical there. In the early part of the solar system, when the planets received their water and atmosphere and so on, then Mars had an ocean, and Mars had a much denser atmosphere, and Mars was once much warmer, and et cetera, et cetera. But if Mars is only 11% the mass of the Earth, it simply cannot retain that on a long-term basis. The gases will be stripped off. Next slide. See, so what we end up with here is, here's Mars. Now it's very cold after it's had all of its gases and water stripped off. It has a very, very thin atmosphere that couldn't possibly have water in any kind of a liquid form on Mars. And then look what the atmosphere is. Carbon dioxide, nitrogen, argon, oxygen, carbon. You know, I bet you don't notice what all of those have in common. They are the heaviest known gases. Look up the molecular weight. Carbon dioxide has a molecular weight of 44. That's really robust. You know, and all of the rest of them, they're all heavyweights. All the lightweights are gone. Because when gases leave a planet, they leave in the order of their molecular weights. What we're looking at here is a residue of what is left. And it's leaving. Next slide. Anyway, I told you, I get so wrapped up in Mars, I better not get going on that. Let's get to the Earth. See, and then I throw in this one of the Earth, okay? And the reason I throw this in, real nice, really nice. But here we are in the Earth, and we got our atmosphere, and then you got water vapor in the atmosphere like this, and you have sun shining through it. And then when sun shines through water vapor in the atmosphere, you know, it goes, well, let's have the next slide. See, it undergoes photochemical dissociation like this. And hydrogen is produced, and then the hydrogen leaves, and oxygen is produced, and oxygen becomes part of our oxygenated atmosphere, and they estimate that about 1% is of our oxygen is produced in this kind of a way. Now, you can look up, there's various people who have thought about the rate at which this is going on, and you can look it up, and the rates are all over the place. It's a hard thing to estimate, but you can even look it up in the Encyclopedia Britannica if you want. I think the important thing is that it's going on. And if it's going on, then we're losing water. That's inescapable. The only thing you're talking about is the rate at which it's going on. Okay? Now, I'll give you a geological way to measure this, which I would never have thought of. But let me try it on you. Next slide. See, if we look at North America is very representative of the other continents too. We have the broad, flat areas in North America, and this is largely included as this tan pattern here, like this, where there's a kind of a thin veneer of sedimentary rocks over this. Sedimentary rocks are rocks which form at the surface of the Earth, see? And when I say thin, this may be up to 2 miles in thickness. So there's a thin veneer, plus it covers a lot of the other regions too. Now, what most people would be stunned about is most of these sedimentary rocks are marine. They're deposited in the ocean. You can collect marine fossils in Iowa. You know, let me show you a little bit of geological history here. I kind of put it into a map and then a table. Next slide. If we go back to Ordovician time, this is about 500 million years ago. There's times in Ordovician time when it's hard to find anything that was above sea level. There are marine rocks for this early part of the Paleozoic. You can find marine rocks in every one of the 49 states and every province in Canada. Easy. They contain marine fossils. They contain stuff we know are marine fossils. Now, I'll put this in a table for you. Next slide. Let's say, if we go to the early Paleozoic, this is 500 or 600 million years ago, there were almost continent-wide marine rocks at one time or another. Almost continent-wide. Okay, now what I would say is, well, that indicates that the average altitude of the continent at that time is below sea level. Okay, we'll start with that. Then when we go to the late Paleozoic, about 300 million years ago, well, there's widespread marine rocks. There's no question about that. But about half of the rocks are terrestrial. They're non-marine. So we got about a 50-50. Okay, then I would say, well, that has to indicate that the average altitude of the continent is just about at sea level. Half marine, half non-marine. Okay, then if we go to the Mesozoic, let's say about 100 million years ago, those widespread seas have disappeared. Instead, we still have an interesting seaway in the Mesozoic, but most of the rocks are non-marine, they're terrestrial. So I would have to say, well, that's interesting, but the continent must have at least a few hundred meters of altitude. When we go to the early Cenozoic, the seaways disappear. And instead, we just have the very outer parts of the continent are covered with a marine environment. The stuff we nowadays regard as really kind of a lowlands. Okay, so I would say, well, the continent must be at least a couple hundred meters higher. When we go to the present, the late Cenozoic, the continent now has an average altitude of 1 kilometer, 3,000 feet. You know, and I would say, why didn't I ever see this before? Here I've been trying to explain this by enlarging and closing the ocean basins and raising the continents up and all of this stuff. We're losing water. And if you go from 500 or 600 million years ago, when the average altitude is below sea level, to at the present time, when the average altitude is a kilometer above sea level, then maybe you've lost a kilometer of water. Think about that one. Next slide. See, now when you think about that, that's really drastic. I mean, it just blows geologists' minds, okay? But just think about it. You say, okay, the only way you have to add any new water is the impact of comets. The only way you have of getting rid of any water is photochemical dissociation. See? You're limited. Now, what I would say is photochemical dissociation is going on at a more rapid rate than comets are bringing water to the Earth. And therefore, sea level is dropping, and sea level has dropped a kilometer in the last 500 to 600 million years. And that sounds so drastic. Good grief, a kilometer? You must be crazy. See? Okay, well, let's think in terms of like a geologist or an astronomer thinks. And what you do is you say, all right, if you've lost a kilometer and it's 600 million years, why don't you just divide 600 million into a kilometer to see what you lose per year? And what you lose per year is 0.6 of a micron. 0.6 of a micron, see? That is so slow, it's almost unbelievable. Now that has nothing to do with the storage of ice and everything else. We are very, very, very slowly losing water. It's 0.6 of a micron per year. Next slide. Well, look at it, see? Look at those continents. The shoreline is on the edge of the continent, see? Way, way out on the edge, and yet all the continents are all covered with marine rocks. Isn't that amazing? That just amazes me. Why didn't I see this? See, I saw it indirectly through astronomy. Okay? Now, I'm going to have to get another illustration here. And what I would like to do is I'd like to get another one over on this side here, see? A big globe. And what I'd like to do is I'd like to put it like it was in the early Paleozoic. That is, the whole Earth was almost entirely covered with water, and there were only a few little blotches of land standing up here and there. And then I'd put this one in the middle, and then over on the other side, I'd put one for 1 billion years in the future. And 1 billion years in the future, it's going to be as dry and barren as Venus. Next slide. Well, I'll leave you with that happy little thought. And I thank you so much for your interest.
Thank you, Dr. Peterson, for a very thought-provoking presentation. I guess we'd better continue with our manned space program so that we can learn even more about the planets within our solar system and in turn, more about our own planet. One of the OCA's functions, as well as this TV program's main function, is to bring the fun and wonder of the night sky to the general public. If you don't have a telescope or don't know where to start, but you'd like to learn more about astronomy and the enjoyment it can bring, please access our website at www.ocastronomers.org for upcoming public outreach events throughout Orange County. You'll find the OCA membership friendly and very helpful. Our website has additional information about the activities the club has to offer. If you're interested in attending one of our star parties at Black Star Canyon or our ANZA site, please send an email to lookuptonight@ocastronomers.org. Thank you again for joining us this evening. We're looking forward to seeing you at our March meeting, and that will feature a little old me, as I'm the What's Up presenter. Chris is taking a break this month. I think he's earned it. And our main speaker is Dr. Louisa Riebel from the Spitzer Space Telescope project run from Caltech JPL. Also, please take note that due to circumstances beyond our control, the meeting in April has been changed from April 9th to April 16th. Till next time, get outside and look up tonight.